In this video, we're going to take a look at this 100 watt LED driver in closer depth using like 5 different kinds of LEDs. We've got red LED, green LED, blue LED, white LED, and amber LED. And those are them on the bottom, right there. And they should have different varying forward voltages. This is what the manufacturer specifies. The red one is much lower than other 4 LEDs at 18 to 22 volts. All the max forward currents for all LEDs are 3.5 amps. So I'm going to check them from on the current ranges on the driver, just so we can figure out what the switching frequency is for the LEDs and how it changes based on the current through the LED, which it should. And this is also to check to see how robust the driver is, because it'll have to change the forward voltage to get the right current out of the LEDs. Because it's a constant current driver, it's looking at a current through the shunt resistor, so the forward voltage should be change based on the forward voltage of the actual LEDs on the die. For the setup, I've got a 48 volt 7.3 amp power supply connected to the LED driver directly, and then just some alligator clips coming off the LED driver. And I'll just be connecting the LEDs up to this heatsink. It's just a temporary measure, so this heatsink shouldn't get too hot. If I was actually going to run this for an extended amount of time, I would get a much bigger heatsink to connect the LEDs to. But this should just be sufficient for this little test that I'm going to do. Alright, let's get some heatsink compound on that block. I'm using the Ceramic 2 by Arc Silver. It works pretty good, and it's non-conductive paste, so that will work good for making sure the contacts don't short out. Alright, let's just test the white LED first. Okay, that's that. Let's get this LED driver. One more. Okay. Now this is set at 2.5 amps. And I should probably face this away just so it doesn't make the camera all mad and messed up. Alright, let's turn the LED now. And there we go. Oh, it's just very bright. And it's all working fine. So our test setup is correct. Okay, now let's check the forward voltage of the LED. And this is at 2.5 amps. It's sitting at 38.2 volts. That LED block got hot and just that little, it's about 50 C in just that little bit of time that the LED was on. Wow. And the LED driver is cool to the touch, but the heatsink is surprisingly hot. Okay, well, I took all the measurements for 2.5 amps with all the 5 LEDs. I actually measured the current too, which is what I added later. But the switching frequency is right here, and the forward voltage is in this list right here, and also the forward current at the specified 2.5 amps. So for the red LED, yes, it was much lower than the other LEDs. Sitting, the forward voltage was 22.2 volts compared to around 35 volts for all the other LEDs, with the white LED being the most forward voltage at 38.2 volts. All the colored LEDs are sitting around, about 34 to 35. And this would vary depending on the 100 watt LED that you use too in the manufacturer. This is just for a general ballpark figure. For the forward current, it was all pretty close to 2.5 amps, except the red LED, which is sitting at 2.43 amps, which is it's pretty close, and it might be due to the increased switching frequency, which is on this chart right here. As you can see, and this is in kilohertz, as you can see, the white LED had the lowest switching frequency at 108 kilohertz, while the red LED had a really high switching frequency at 273 kilohertz. While the color LEDs, or the red, blue, and amber LEDs, were sitting around 160, 150 kilohertz. This result seems almost counterintuitive. I was expecting that the white LED would have the greatest switching frequency, while the red LED would have the lowest switching frequency. It seems like it should be the other way around, but it isn't apparently. And I have a little theory about this. It might be due to the design of the LM3409 chip. So this is page 10 of the LM3409 datasheet, and it describes how the sense line works and how the it measures the constant current of the device. It uses a peak current control circuit, apparently. So here's the voltage in, and this sense resistor, the P-channel MOSFET, an inductor, the recirculating diode, and there's the LED terminals right there. So why the switching frequency is higher for the red LED, I think that it ramps with the voltage on this node, and since the red LED is at 22 volts, it reaches the set voltage quicker than the other LEDs, and then it ramps back down, and when it turns on again it ramps up back up. And I've exaggerated this. I think it would be like that. Let's get rid of that. It would just be like that once it hits the equilibrium point. since this red LED is so much lower than the other LEDs, it has a higher switching frequency. That I stand to be corrected on this. It's a very complex circuit with all this different stuff going on, so there might be something else at play. How the sense circuit works is it measures the differential voltage between these 2 points, and they've calculated this out to be 2.48 or 248 millivolts. So when 248 millivolts is across this sense resistor, it turns off this P-channel MOSFET. And doing so, it stops the voltage coming in, if you could say, or the current going into the node. And before that, the energy was being stored in this inductor like that way. And now, since the voltage source is disconnected, essentially, the MOSFET, or the inductor, tries to keep its magnetic field, so it reverses the voltage polarity. So current keeps flowing through the LEDs, even though the switch is off, because of the stored energy in the inductor. And that's what this recirculating diode is for, is so it keeps the current flowing in a loop to keep the LEDs on, and also to keep this voltage right here from damaging the LEDs, since it can be pretty like in the hundreds to thousands of volts at the worst case. So when the voltage reaches a lower threshold, the MOSFET turns on again, and then this diode is reverse biased. So this diode turns off, and this inductor starts storing up charge again, and the voltage on this node starts ramping up again, and then you end up with like a jagged kind of noise on this LED, on the LED current. So that's just a simple, well, just a top level view at how this device can control the constant current through the LEDs. So what I'm doing with the LED driver is I'm making it adjustable by adding optional resistors in parallel with this main sense resistor, and effectively it would change the current going through the LEDs. So 2.5 amps, 3 amps, and 2.5 amps. So I just have two resistors at the bottom of the PCB that change the LED current, because it changes the resistance of the sense resistor, and the parallel resistors will lower the resistance of this, making the voltage, the current going through the resistor have to be higher to equal the same amount of voltage to shut off the gate. So that essentially increases the amount of current going through the LEDs based on the resistance and the change in resistance. So that was just a quick look at the circuit that modulates the current control circuit. And this switching frequency might depend on other things in the circuit too. So I'll just finish up getting the data and then look at the results from there. Through my calculations, I found that 0.47 ohm resistors fit almost perfectly, that if you solder one on, it changes this 0.08 ohm resistor to make 3 amps. So it would, once you solder one resistor on, the total resistance of the current shunt will make the LED driver output 3 amps, while soldering two resistors on makes the LED driver output 3.5 amps. So since it lowers the resistance each resistor you solder on. And this path isn't very high power, since these are like about an order of magnitude higher resistance than the main current shunt resistor. So there isn't much current flowing through this section of the circuit. So I'll just solder up this resistor on quick. Just gonna put a little paste on just to stick it down with. I like to use this little, you can find these on Amazon, just little needles. I filled it full of full of flux. This is like gel flux, and the tip isn't sharp, by the way. It's just like a blunt tip. But it works good for applying little for flux and circuits. It's got a very controlled application. You can control the application speed really good. This little dot. Stick down the resistor. Alright, there's the current shunt resistor on, and that's going to allow the LEDs to run at 3 amps now. Might need to upgrade the heatsink. Okay, I'm done with the 3 amp one now, and it looks like all the switching frequencies have dropped by about around 60 kilohertz, 50-60 kilohertz. So that's pretty interesting. I wonder what the white one is going to do at 3.5 amps, because it might, yeah, look at that, it might be only 15 kilohertz, and that's in the audio frequency range. So that might be a problem with the driver, that it can go in the audio frequency range, so at 3.5 amps. But I don't really recommend running the 100 watt LEDs at 3.5 amps, just because you're kind of running them at their max, and 3 amps is much more safe value to run them at. Alright, well the voltages all have increased by just a few volts, just around, the white one actually decreased. That's really strange. Let me remeasure that one, because that's probably a higher voltage than the 2.5 amp one. And the current is right around 3 amps, like expected. Okay, well the voltage, instead of 37 volts, I remeasured it, now it's 39 volts, and that's much more expected result. So I'm just going to solder another resistor for the 3.5 amps and see if it can do all 3 current ranges to perfection. Okay, well I got the other resistor soldered on now, and let's test it out at 3.5 amps. Okay, well, it seems this heatsink is inadequate for the job, since the LED it gets super hot just after about 5 seconds at 3.5 amps. But I didn't hear any audible frequency, so it must have still been in the over 20 kilohertz, the switching frequency. It's just that this heatsink is way too inadequate for the amount of heat that the LED is dissipating. And I found this out by, it would always just lift up a little bit. It's not there's no screws forcing the LED down, so it just pops up a little bit and then it loses all thermal contact to the heatsink. And what I found that is that the current actually increases past 3.5 amps, which I believe that it is because the LED is warming up so much that the resistance of the LED goes down substantially, making the LED driver do some strange things, I guess. But with a bigger heatsink, hopefully we should get some good readings. When I pressed down the heatsink when it was running, it looked like the current was leveling out at about 3.58 amps, which is pretty close to 3.5 amps. But when I just left it off, it went up to 4 amps, and that's not very good for the LED. And it got really hot too. So I'm going to leave that for another video. Testing the LEDs at 3.5 amps on a much bigger heatsink. But we got some good results for 2.5 amps and 3 amps. We got the switching frequencies. We found out that the switching frequency decreases with the increase in current, as you can see by the downward trend, and the switching frequency increases with the lower forward voltage of an LED, which is pretty interesting too. And we also found out that the current shunt resistors are pretty spot on. We're off by just a few percent error. Like this 3.05 amps, it should be 3 amps, but it's off by 50 milliamps. That's not too big of a deal. It's only 50 milliamps, so that's pretty close. The largest error was this 2.43 amp for the red LED, which is just 70 milliamps off, which is a very nice result right there. And also for the 3 amp one, it's 40 milliamps off, which is almost spot on. And the forward voltages of the LEDs, the red one is measured to be 22.2 volts and 22.5 volts for 2.5 and 3 amps, and that seems to correspond with the manufacturer's data sheet. And all the other ones are within the range too of the data sheet at 2.5 and 3 amps. So it'll be for another video, I think, because this one's probably been going on long enough. So stay tuned.